Welcome to this demonstration of the JEDI planning interface developed by the Autonomous Agents and Intelligent Robots Lab at Arizona State University. In recent years, significant advances in the fields of robotics and artificial intelligence have opened up an entirely new landscape of possibilities for how machines can be used to enhance human lives. However, most current AI and robotic systems are difficult for a layperson to interact with and understand. To mitigate this, JEDI is being developed to facilitate outreach efforts in helping people understand how to give AI systems new tasks, debug those systems when things go wrong, and understand the capabilities of those systems. JEDI addresses the difficulties in AI outreach and education for the case of AI systems that can use symbolic planning to take actions in an environment. It does this by providing a user-friendly interface with human-friendly language that requires no expertise in order to interact with and learn more about such AI systems. JEDI overcomes three technically significant challenges in making AI planning more accessible. The first challenge is the fact that inexperienced users will have no knowledge of the constraints that real robots need to conform to, nor of how robots actuate their individual parts to achieve high-level goals. In this context, that means users will be reasoning about planning problems at a rather abstract level, and will need to be shown high-level action names like pick up plank 1, rather than the low-level numerical inputs a robot would need to actually perform the action of picking up plank 1. The second main challenge follows from the first. Even if we can show users abstract representations of the robot's capabilities, that isn't much help unless we can efficiently convert back from high-level plans made of abstract actions to low-level motion plans suitable for execution on a robot. The third important challenge addressed by JEDI is helping users to understand a planning problem better without needing to have an experienced human on hand to alleviate confusion in real time. Doing this requires having a system that can compute personalized explanations automatically, taking into account what the user is most likely to understand or not at the time of explanation. Now let's check out the systems that allow JEDI to overcome these challenges. JEDI is built from a few key components that work together with the Blockly visual programming interface. The first component is a task and motion planning system to handle conversions between high-level and low-level actions. This system addresses the first two technical challenges in letting inexperienced users interact with non-toy robots. The next component is an algorithm for computing personalized explanations for plans that fail, to address the third challenge of helping users better understand planning problems in an automated way. The final main component of JEDI is a straightforward but effective strategy for converting generated statements about planning domains into some semblance of natural language. Let's dig in a bit more to each of these components before moving on to a demonstration of the system in action. The Task and Motion Planning System ATM-MDP, developed by our own lab, handles the refinement of high-level plans provided by users down to low-level motion plans. This enables JEDI users to interact with and learn about the capabilities of real robots in simulated 3D environments. JEDI asks users to put together action plans with visual blocks to solve problems, but it can be hard for the novice planner to meet every necessary condition on the first try. So when users submit a failing plan, JEDI displays an explanation that tells them what exactly went wrong, whether some goal condition isn't achieved or some action in the plan has an unmet precondition. Coming up with useful explanations for failed plans automatically is a non-trivial problem, and JEDI handles it by using an algorithm that computes explanations while remaining sensitive to the user's level of understanding of the problem, insofar as that understanding, in the form of a planning model, can be gleaned from the content of the submitted plan. One of the barriers currently standing in the way of anyone without an AI background that nonetheless wants to understand and interact with planning agents is the formality of the symbolism used by these agents. JEDI deals with this by tying actions and predicates in a domain to snippets of natural language that can be combined into coherent sentences. This allows states and actions to be expressed in a way that is less intimidating to users who don't have much exposure to concepts like predicate logic. So what exactly is JEDI and what can it do? JEDI users first need to pick a domain and a problem to work with. We currently have 4 domains to pick from, with a total of 8 problems. More domains are on the way. Each of these pre-made problems requires instructing a manipulator robot to arrange 3D objects in a particular way. For this demonstration, we'll check out the Kiva Planks domain and its 3π problem. After picking a problem to work with, users can enter the training area, where we find the drag-and-drop Blockly interface embedded. This interface allows abstract actions, represented by visual blocks, to be stitched together into a plan. An image of the goal for the current problem is shown here, while the goal is spelled out more explicitly up here. As you can see, for this problem, The goal is to stack these 9 planks so that they take the shape of 3 pi symbols, one on top of another. Users also have access to a 3D simulation of the robot and the environment, which shows the initial state of the problem. This window is also where the robot carries out successful plans. But before we look at a working plan, let's see what happens if we submit a more naive plan to JEDI. The Load Workspace functionality will come in handy for this. This plan tries to place the 9 planks in the shape we just talked about, but does so without picking any planks up first. As you can see, we're told why this plan can't work so that we can fix it. To further help users triangulate on the problem, the offending action is highlighted as well. At this point, users would normally begin editing their plan to fix the problems described in the explanation. But for this video, we'll just load in a successful plan directly. Once we submit a valid plan that achieves the problem's goal, the Task and Motion Planner is called to refine those abstract actions into a concrete motion plan to be executed by the robot in the simulated 3D environment. When the Task and Motion Planner finishes computing a solution to the plan, we can watch the simulated robot execute the actions in that plan. Different domains involve robots with different form factors, and puzzle-style domains can include non-physical constraints on how objects are allowed to move. JEDI also comes with documentation and a video tutorial to help users get started. We hope you've enjoyed this glimpse at the future of AI outreach and education. Visit our lab's website to access JEDI and to learn more about our efforts to make AI methods safer, more reliable, and more generally useful.